We're going to start with a review of complex numbers. To skip this review and go straight to the solution, click the link in the video description. If z is our complex number, it's equal to a plus bi. Then the conjugate of z, which we write as z bar, is a minus bi. The magnitude of z is the square root of a squared plus b squared. If you take z and you multiply it by its conjugate, you also get a squared plus b squared. So the square of the magnitude is equal to the complex number multiplied by its conjugate. The conjugate of z plus some real number, for example 2, we can write this as a plus bi plus 2. We notice that taking the conjugate doesn't affect the real part of a complex number. So we can just take the conjugate of the complex part and add the real part to it. So let's solve the problem. We are asked to find z plus 6 over z that satisfies this equation. And we notice that all the possible values for this expression, they're all real numbers. So substituting a plus bi for z and simplifying, let's collect the real terms and the imaginary terms. This expression, again, is a real number, which means the imaginary part disappears. This means that b is going to be equal to 6b over a squared plus b squared. Let's take this equation, divide both sides by b, and multiply by a squared plus b squared. We have a squared plus b squared is equal to 6. This is the square of the magnitude of z. It's also equal to the product of z and its conjugate. We can use this now in the equation they gave to us. Let's go ahead and make this substitution. 6 for the square of the magnitude of z. On the left-hand side, we have 72. This is z plus 2 times the conjugate of z plus 2. Z squared plus 1 times its conjugate. Let's subtract 31 from both sides. And again, as described earlier, this is just the conjugate of z plus 2 and the conjugate of z squared plus 1. Let's multiply these out and let's subtract 1 from both sides and expand a little bit more. Let's take a look and see what we have. We have z plus the conjugate of z. Then we have the square of the product, and we have these individual squared z terms, and then this product here. So I think I want to write these two terms, because when I do that, I'm going to end up with the square of a binomial. We have this 8, and this is actually the square of z and its conjugate, so I can replace that with 36. This comes out nicely because now this is the square of z plus z bar, and then I have 4 times z plus z bar. 8 plus 36 is 44. I'm going to subtract 40, and I'm going to be left with 4 on this side. To make this a little bit easier to see, I'm going to substitute. We'll let w equal z plus the conjugate of z. So this becomes w squared, 4w, and 4. This is also the square of a binomial, which means w is equal to negative 2, which is the sum of z and the conjugate of z. Now, if we want, we can substitute z and the conjugate of z and set that equal to negative 2. And again, since we figured out that the square of the magnitude of z is 6, a squared plus b squared is equal to 6, and substituting, we get b squared is equal to 5, and b is equal to root 5, so z is equal to negative 1 plus I times the square root of 5. We could substitute this in for the expression z plus 6 over z, but you might see a shortcut. We found earlier that the product of z and its conjugate is 6, so we can actually solve by dividing both sides by z for 6 over z. This is equal to the conjugate of z. I can substitute that up here. This is equal to z plus the conjugate of z. And we already found that up here, and we know that it's equal to 2. This is option A in the problem statement.